the radical halogenation of an alkane. So this reaction is important for us as organic chemists if we are trying to do any synthesis that starts with an alkane. So what we're talking about here is a molecule that is just an alkane that contains absolutely no other functional groups. So that would be a hydrocarbon, so something containing only carbon and hydrogen with all carbon-carbon single bonds. And so alkanes are very unreactive molecules. And this is the only useful reaction that you will see for an alkane. So as an example, I'm going to start with methylcyclohexane. So we can see when we look at the structure is we don't have any pi bonds, right? Because it's all carbon-carbon single bonds. So this reaction cannot undergo the reactions that we have seen previously with alkenes and alkynes. It also lacks any sort of leaving group to undergo a substitution or elimination reaction. So what we're doing when we're halogenating is we'd be introducing a leaving group. So there are two halogens that this reaction will work with. We can do a radical halogenation with chlorine, or we can do a radical halogenation with bromine. And so we are going to focus solely on the radical bromination, and that is because it is a more selective reaction, which means it's more easy to control exactly where the bromine will be introduced into the molecule. So we are going to focus only on bromination. So with this methylcyclohexane, I want to introduce a bromine via this radical halogenation. So we're going to use the molecular bromine. And to get the radical reaction initiated, we need either light or heat. And I'm actually going to say light and or heat because sometimes you will see them both used together. And you won't be responsible for distinguishing when you use light, when you use heat. Just recognize if you see either of those conditions, what's with the bromine, what sort of reaction we have occurring. So this is to initiate the radical reaction. So what do we mean by initiates radical reaction? So a radical is a lone electron, an unpaired electron. So we don't see these very often. And so that is what's being generated in the first step of this mechanism. So if we have molecular bromine in the presence of light and or heat, what we're going to have, and we want to control this, we don't want to have too much light or heat, we want to generate just a small amount of bromine radicals. So we're not taking and transforming all of the bromine to radicals, just a small amount, and then it's a chain reaction. It's going to keep on propagating and continue. So what happens is the bond between the bromine atoms is a weaker bond, and it can cleave, giving one electron to each bromine atom. And so this is going to form two bromine radicals. And so this is known as an initiation step. So an initiation step in a radical reaction is any step where you start with no radicals and you form a radical. And so the next thing that's going to occur is that bromine is going to abstract a hydrogen from somewhere in your alkane. And here's where the selectivity comes in. Bromine is less reactive of a radical than chlorine, which means it's a little bit lower in energy, and it's going to be more selective to forming the most stable radical that it can from your alkane. So if we draw our alkane, the most stable radical that we can form from this alkane would be a tertiary radical. So on the alkane, we have secondary carbon atoms, we have a primary carbon atom, and we have a tertiary carbon atom. The stability of carbon radicals is analogous, follows the exact same trends as the stability for a carbocation. So like a tertiary carbocation, a tertiary radical would be more stable. So one of these bromine radicals, and where this is a chain reaction, we don't keep track of stoichiometry. We're just going to use what we need for that step. So this bromine radical is going to abstract a hydrogen where it would form the more stable tertiary radical. So it is going to abstract a hydrogen from that tertiary carbon. So what I'm showing here is one electron from this bond and one electron from the bromine coming together. So that'll be 2-electron bond or a covalent bond. The other electron from the carbon-hydrogen bond will be transferred onto that tertiary carbon to form the tertiary radical. So here is the tertiary radical. So this is what we will preferentially form if we have a tertiary carbon in our starting alkane. And we're also forming HBr. So this sort of step where we start with one radical and we form a different radical, this is known as a propagation step. So all radical reactions will have steps that are initiation steps, and they will have steps that are propagation steps. And finally, they'll have steps that are termination steps, where two radicals come together and overall the radical concentration is decreased. Okay, so this tertiary radical is what's controlling the selectivity of this reaction, because this is going to be more stable than a primary radical that would form here or in any of these secondary carbons. And so the next thing I'm going to show is another propagation step that will also give us the major product of this reaction. So if this tertiary radical reacts with another bromine molecule. So remember, in this first step, we only converted a tiny amount of the molecular bromine to the radical. So we still have bromine, molecular bromine in the solution. So if it reacts with the molecular bromine, so we can form a bond between this carbon atom, and if I take one of the electrons from the bromine-bromine bond, I'm implying I'm making a new bond between the carbon and the bromine, and then the other electron from this bond is going to form another bromine radical. And so what we have done overall is we have replaced a hydrogen on that tertiary carbon with a bromine. So this would be the desired product that we would be looking for from this radical halogenation reaction. So I am going to draw it in up here. Okay. And we are going to put a box around this to kind of emphasize what the overall reaction is that you're looking for. So overall, if you're looking to give the product, you're looking to replace the hydrogen on your alkane with a bromine, and specifically you're going to replace the hydrogen that would form the most stable intermediate. So that would be a tertiary radical if possible. If not, then a secondary radical, or finally a primary radical would only happen if you only had primary carbons. Okay, so this step here, we formed the carbon-bromine bond, and we also formed another molecule of bromine radical. So because we started with a radical and we formed another radical, this is also a propagation step. And if we were asked to draw a mechanism that leads us to product, we could stop here, because we could assume that once you form this radical, it can just come on back up to the step before it and keep going through the reaction sequence. I do want to show you one more step, though, to show you the last sort of step that you would see in a radical reaction that's possible, and that would be a termination step. So if our alkane radical, I like to draw steps that are productive leading towards product. So if this were to encounter maybe a bromine radical instead of a bromine molecule, what we could have take place here is these two radicals could simply come together. So what I'm indicating is that this electron and this electron are going to be forming a covalent bond between the carbon and the bromine. So this is also a step that leads us to the product that we were looking for. And we're not generating anything else. We're taking two radicals together and forming a covalent bond, so we are decreasing the concentration of radicals. So this sort of step is known as a termination step. And so there are actually a lot of things that could take place in this reaction. You could really imagine any radicals that you form at any point in time coming together in a termination step. So there's really actually a lot of byproducts that would form in reality. So what we do is we focus on what it is that we're looking for. And so we're always going to be asking you to draw the monohalogenation product. So assuming that this reaction only occurs once and you only replace one hydrogen at the more substituted carbon, right? So the tertiary carbon preferentially to form an alkyl bromide.